after mathematical physics.
Okay.
Cool. Because I have no idea what what to expect.
I have so many.
Okay, cool.
There is two parts, so one portion is online. Have you seen the manual?
I briefly read the manual.
Yeah. So you can make announcement to complete the online portion before coming to class. In person part, just get the car,
Okay.
distance and time.
Alright, well, in case you want to go anyway, just to get more, we can make a little video of it, and then, for future reference.
Yeah.
I don't know. That's like the main reason why I want to do it.
Well, after the class we can.
Yeah.
So, the due date of mathematics homework.
Yes,
I forgot to bring.
Hmm.
I forgot to bring. I have done.
I'm sure you can just ask her to turn in tomorrow.
Yeah.
Yeah.
But he has option. Then tell. Then
Yeah.
post on the blackboard.
Yeah, sure. Yeah, you can just turn it in today online.
So
So,
you don't need to cross the debate.
yeah, right?
Yeah.
So, everything's still, within limits.
Option is here. And how your preparation is going for Wonderland?
Something I feel pretty good about. I don't really want to put too much time into thermo because I don't want to, I don't know. I guess over preparation is the thing, maybe. I don't know.
Should have problem solved about SSM? Your SSM problem?
Yeah.
Good.
Because it is clear, so I will get the eventually.
When?
Within the week.
That's good.
Yeah. And congratulations to you.
Thank you.
Yeah. This is security now.
Yesterday you were there? Yesterday?
Yeah.
So you did.
I will enjoy this.
You missed the class.
I will finish it out. Water number, discussion of what
Thank you.
Yeah, it gives me very, I think, it's been, I've had it for forever, but at least 2 years, maybe 2.5.
So it's, I think it's sufficient for all day. And you and RC.
Yeah, it's good to have this whenever. I don't have to worry about rain. Some days it's really
I used to learn a lot of
Yes.
because I have
Then
one stone problem.
Any sons?
Highly fast. You need to check and what.
no, but then I had the cold and also
Less
because
than
difficult for
four
me.
hours.
Second part.
I had
Drinking
one.
a lot.
Second class I have done
Clear.
acids.
I had one of those
Yeah.
maybe 7 years ago.
I have
Yes. I haven't had one
it's
since.
like
But-
very question about
Have you had surgery or?
First class, right?
No.
What else?
It was just a minor thing. I have a kidney disease hereditary in my family on my dad's side. So maybe that'll be something I have to deal with in the future, but
I think
That's all right.
life
life is much more meaningful if you know it's shorter, but I don't know. That's fine.
If you study the field, that's how That's what the room has.
You can just clear.
Yeah.
Everything is fine.
Okay. Done. Person English today. Okay.
Brilliant guy.
Yes, he's gonna pass all his qualifiers.
Okay. Let's summarize how we apply the Lagrange equation of motion to solve the problem. This is a strategy I already discussed last time, and we spent a few moments, right, to solve one example. Now today we will solve another 2 examples and see how can we apply this. So now let's start from one more examples is first. So this example is adverse problem machine. So this machine is we have a pulley and maybe a radio, and then we have a tree M1, M2. Okay. This we call the output machine. So now let's consider this case. Let's consider if the poly, the poly is assumed. Poly is assumed. Okay. Fractionalist and massless. Let's consider this case first. Okay, and now they found that we analyze the dynamics. Analyze the dynamics of the system, right? So that is the question. Now we will want to ask first here. So first step, we are going to analyze string. Okay. So now let me first use the dot. The analyze constraints are constant, right? In this case, how many constraints? Here. Okay. So we know this strip is length L is fixed, right? Whatever the M1 up and down. So we have okay. We need to set up. So to find the formula here, we need first set up the coordinates such that we can express this. So now let's set up this one as a real. So now let's say I'm going to say this is x1. X1 is the distance from M1 to the center of this poly, and x2 is the distance of the M2 with respect to the center point. So that is the setup this first. Okay. Now, what is condition? We know x1 plus x2, right? So this plus this and plus the half of this to be equal to L, right? Pi r equal to L. So that is condition. Do we have more? I think that's all, right? So, or if you want to write down in this way, so that is x1 plus x2 plus pi r minus L equal to 0. So alpha equal to 1, right? We have only, okay, k equal to 1. Okay, so we have only 1, so k equal to 1. Only 1 equation constraint. So that is the first analyze. Second, then we're going to choose the general coordinates, right? How to choose first we need to find how many the independent or degree freedom, right? Then we can select how many independent the general coordinates, right? So n, that's degree freedom, we already define in general here, right? So now this is formula. But in this case, we know it's only one dimension, right? So this will go to 1 multiply how many system? Here. Since this pool is massless, so that we can ignore. So only is 2, right? Now 2 minus 1. Right? K is 1, n is 2, and 3, this is dimension. In this case, only one dimension, right? So that is 1. Now we only select 1. General coordinates enough to characterize this system, the motion or dynamic of the system. So that is only one independent. And which one we are going to select? It's R3. And now, we are going to choose X as a general coordinate, as a Q. That means this is this one, right? So that I'm going to select equal to X1. So that means I'm going to select general coordinate X, which is equal to X1. Then if that is the case, okay, that is I choose this as a general coordinate, which is a Q, right? And third one, so once we select, then we are going to write this transformation equation. Equations. Like all this position of each particle, it's a function of general coordinate. It's velocities, we also function of general coordinates and general velocity, right? So now we have how many? We have 2, right? So now x1 equal to x, as we define. Then x2. How to determine x2? From here, right? Yes. X2, so I move all the others, so L minus pi r minus x1, right? Okay. Now, once we do that, as I said, let's immediately do this one, since we are going to apply to the kinetic energy. We need velocity, right? So now let's do x dot is, sorry, x1 dot is x dot. You have a question? Okay. And x2 dot, this constant, right, is minus x dot. Is minus x. Oh, sorry. Yeah, here you can replace x1 by x. So, yeah. So just middle dot is minus x dot. Okay. So we finish this. We have the transfer. Now we are going to go to write down the kinetic energy and potential energy in terms of general coordinates. Then we are going to write down the Lagrangian and apply the Lagrange equation. So now, number 4, T and V, right? So we are going to write this. Let's first write down the kinetic energy. So kinetic energy, okay, that is half of m1 x1 dot square plus half m2 x2 dot square, right? We need also calculate this one. It's okay, yeah. I have a rotation, right? Yes.
Choose 3n minus k equal to.
Okay. Yeah, because this is a 3-dimension, right? This is
Yeah.
3D. But here we have only 1D.
1D.
So this number actually depends on system in which you select.
Yeah.
Because that's also ignore z equal to 0. There are 2 ways. If you add more as a constant equation, then you have 3 equations. So here is 3 or 2 minus 3, right?
Like, how do you get that two? Instead, like
The 2 particle, n equal to 2.
Oh, okay.
2 system, right?
Yeah.
It's
Okay.
2.
But that 3 means for 3 dimension and.
Okay,
can
here
use
you
one-
have,
yeah.
actually you have another 4 equations I didn't write up here. Right, so if in that case, then you have a 5 here. Then the 3 multiplies to 6. 6 minus 1, minus 5 is 1. So this is implies, sometimes you have experience, you know, okay, so this one I always say, it's really depends. This is degree of freedom for each particle.
Yeah.
So if your select system is only one dimension, you just select one. Or two, you select two. Or three, you select three. But this one is really depends. So, but this one is also depend on how you select this one, right? If you select three, you have to include all the others. Yeah.
Thank you.
Okay. Yeah. All right. So now let's. In principle, now I'm going. Let me write down here. Then there's a rotation of Pauli, right? If I say this M3. Here, M3 to 0, in this case, massless, right? M3 R square, that is rotation, right? If it's considered angle, that is this one, right? This is 0, so this term is 0. So that is only the first two terms, because we have this condition massless. Then now we are going to substitute here. X1 dot square, x2, that is first term half of m1 x square, dot square, right? X1 dot square is x6, but x2 half m2. X2 dot square, even though x2 dot is minus x dot, but the square is still positive, right? So, okay, so this is a simple, just a half of m1 plus m2 x dot square, right? All right, so that is kinetic energy. Now the potential energy. Potential energy, as I read down here, external potential plus internal potential. So let's look at external potential. In this case, which is external potential, gravitational potential, right, for each one. Consider reference with some reference, if reference here or reference to Earth's surface, right? So we have, let's write down the external one. The first particle has external, second, the block or internal, and some of internal, right? Internal, so now if we select this potential here is 0, then this is a distance below this 0, right? So negative, this was negative. This one will be 0, right? Because gravitational. So here, then I just consider these two, and then the internal is interaction between these two. Consider that the gravitational potential from Earth is very big, right? So we just consider this is almost 0. In most cases, we just ignore, because we know the gravitational potential is the product M1, M2, right? M2, the product is much, much smaller than M1 multiplied the mass of Earth, right? So that is the idea why we immediately write down here instead of to ignore this. Now the first one, if we select this one, 0, so that is minus M1 G, right? H1. H1 is X1, right? And the second one, M2G X2, right? That is the potential. As this is 0, so the below 0 is negative. Okay, now you are going to substitute X1, X2 in terms of general coordinate X, since we select X. So that is minus M1GX minus M2G. Now X2 is this formula. So that is L minus pi R minus X. Okay, so now the potential energy and kinetic energy we have write down. So now we go to, and also this is already function of general coordinates, right? It's T of X dot function. This is a function of X, right? Only X, no X dot. Okay, now we go to here. We are going to write down the Lagrangian. So L is T minus V. Now we substitute T is half of N1 X square. This is sometimes the sign, because this is minus V, and V already minus the plus, right? Plus here, M1G X plus M2G L minus pi minus pi R minus X. Okay, that's the Lagrangian. Very easily now. Once we have the Lagrangian, we are going to do the partial L, partial X. Since this term, right? We need to find these two terms and substitute into this equation. Partial L, partial X is this one. So now, let's do This is only function of x dot, right? So it will not relate to x, only this one and this one. So now first one is m1g. m1g, right? Partial x. And the second one, these are constant, so it's only negative mg2, right? Okay, so that is the partial L, partial x, and then partial L, partial x dot. This is the only first term. So that is half is cancelled, so that is m1 plus m2 x dot. Okay, now finally we are going to apply the Lagrange equation. Okay. So now d dt inside the partial L partial x dot, I just use this number here, this result here is m1 plus m2 x dot, right? That's the first term, and then minus partial. So now here we have another, again the minus. So here this minus became minus m1 g minus m2g. Yeah.
But
Yes.
if the pulley had a mass and no friction, still that part is going to be 0, right?
Which one?
That part?
This one?
M.
Yeah.
If the
Yeah.
pulley had a mass, and
Yeah, this is 0, so yeah.
if it had a mass, but
If
no,
yes, that I leave the question you consider, if not 0.
but if it had a mass but no friction, then it is still 0, right? Because it won't rotate.
You no fractional, right? No fractional.
I think it. I have.
You consider there's no rotation, right?
Yeah, because with the mass, no.
Q,
friction.
yes. If yes, you are right. Yes. If without any rotation, yes, that term is also 0. Fractional, fractionless, yes. Yes. That's just yes. You're right. So that's consider this. Okay. Let's see. All right, I think here. Right. So now we need to go further to do this total time derivative. This becomes this total time derivative. So here m1, m2 is a constant, right? Then this total time derivative is double dot minus I take the constant outside m1 minus m2g equal to 0, right? Because in this case, there's no any other non-conserved force. There's no such, right? All force is just the gravitational force is conserved, so that's be 0. Okay, then very easily you can show because those are constant, so immediately have this one is m1 minus m2 g and m1 plus m2. This is a constant, right? So because this is all constant, so you can very easily get this one. You can assume that is a, so that is m1 m2 g m1 plus m2 t, right? We just do the integral, and then if for x, I didn't add this. Maybe you have x now, the initial velocity, and then this you do the second integral again. So you have half m1 m2 t squared m plus x plus sorry t plus x naught, right? So because this is a simple in tutorial, I mean the first level of mechanics, you know how to solve that. So the key is here how to build up this. That is what we want to remember this. Okay, next problem is a little challenge. So now let's work this one. Okay, example 3. Example 3 is, let me get the picture and then you just correct question here. So this is two dimension, you just consider plane, so not vertical, right? Y, X. Now we have a wire, and we have a bead inside. The wire is maybe rotation here. About this axis, and you just consider this the horizontal plane, right? So that is angle is omega t. Uniform. So here this is constant. That means the wire is uniform rotate. It's a constant angular velocity, but bead is inside. So bead will move, right? And then ask her to find this to solve this dynamics. Okay, so that is and, a bead sliding a uniform rotating wire. In a force free. Force free space. So when we say force free space, we ignore this, or we consider this planar. So this gravitational force is, or gravitational potential is constant, right? So that is that. So it's fine. The equation of motion of B. So what is the dynamics or equation of motion for this? That is question. Now we go to the solution. Again, we follow this. First, analyze the constraint, right? Of course, we say all the constants be holonomic, right? The first one already holonomic, this one has to be. So what is constraint? Suppose at any times the position of the bead has x and y, right? It's x, it's y, right? So that at any time, because the wire rotates, so the bead, for giving us instantaneous time, we can find its position x and y has a relation with that. Okay, so y to x is this angle, right? We know this, that any time, this is a time for given time, right? And that is omega t, right? So you see here, and in this case, you can write this way. So f is y minus y over x minus tangent omega t equal to 0, right? It is holonomic since it's a function of the position, not the velocity, right? And it's equal to 0. But it is also time given explicitly. So this is also real holonomic, geonomic constraint. So we can apply, since it's holonomic, we can apply the following, apply the Lagrange equation. Since in that case, we can find these general coordinates which are independent and replace the coordinates x, y, right? So that is first step. And then how many in the k equal to 1? We have only one equation, right? Okay, now we know you have one equation, so now we are going to find the second one is choose the general coordinate. Now, in this case, again, if I use n equal to, now here I'm immediately use 2 multiplied 1 minus 1. So here, this is 2D, right? Because we just consider planar. And there's only one particle, right? this is n only 1, and this is a k, right? K equal to 1, so now have 1. So means we are going to select 1 as a general coordinate, and this one is arbitrary, which one you are going to select. So now, for convenience, I'm going to, because I know the bead will move only along the y, right? So that this distance change, maybe go to outward or inward, but then simultaneously also rotate. So I'm going to use r. R is this distance. And any position r for given time t, we know that can characterize this vertex, right? So we are going to select r as general coordinates. Or in the GS or GA equal to 1, right? So that is the selection. That is, okay, now we go right down the transformation equation. Equations. So now let's first x. We have 2, right? Here is a vector, right? So I from 1 to n. So each one we have a 3 component. We total have 3 n equations. For n equal to 1, so 2 dimension we have 2, right? So x, if I select r, then x is r cosine omega t, right? For given angle, r cosine is x, right? And y is sine. So you see, the reason why I select r, and I can easily find this transformation equation between the real coordinates and the general coordinates. Then now, keep going, x dot. I think I need space a little bit. So now, immediately let's try to calculate x dot. X dot, r is function time, and this also has a time, right? So we do the first r dot cosine omega t, and then minus r. So when they do this, it's omega, right? Sine omega t. The y dot is r dot sine omega t plus r omega cosine t. Now, when we reach to here, I want to also immediately write down this x dot square and y dot square, such that since we use kinetic energy is square, right? If you write down here and when you write down the kinetic energy, it becomes simple. So now, let's do this. So now here we have r dot square cosine square omega t minus 2r dot omega sine omega t cosine omega t plus r square omega square sine square omega t, sine omega t, right? Similarly, y dot square, r dot square. I think here, no, this is cosine. It's a sine square omega t plus 2r omega cosine omega t sine omega t. Now you see we cancel, right? So that is good. R square omega square.
Sine square.
Cosine. This is cosine
Yeah,
square.
cosine square.
Here, right? Cosine square. Okay. And actually, this is a polar coordinates. So if you're familiar with those, you don't need to write those in details. You can immediately transfer the kinetic energy from Cartesian to polar, right? So that is just for details. But if you have more experience, you don't need to write this intermediate step. You can immediately go to. So now we are going to find. Okay, right? Let's first write down the kinetic energy. Is only one particle, right? This is x dot square plus y dot square. And now here we know this I together, so this two cancels, only this two. And then the r dot square multiply the cosine square of omega t plus sine square is 1, right? So now this very simple, you can know r dot square, the max, sorry. R dot square plus r square omega square, right? Immediately you got this. if you're familiar with the polar, the conversion from the Cartesian to the polar coordinates, you just here eliminate that. You don't need this intermediate step. But if you do not familiar, I want to use step by step. Okay, so now kinetic, and how about the potential energy? As we say, this move in the plane, right? So potential energy, if we set that the plane is equal to 0, or what is a constant? So you don't need variable. Just say it's a constant. Okay, then we have a lot. I think let's go to the next one. Is write down Lagrange and do the partial. This we are going to do, right? So the first Lagrange, T minus V is half of n dot square plus r square omega square minus constant. You will see this constant will not affect our the equation system is when we do how we do this does not do any contribution, right? So now when we write Lagrange, we are going to do this. This is only this term, right? 2 cancel, so n r omega square. Partial L, partial dot. It's only this term, right? So 2 cancel the n r dot. Okay. Then it's a Lagrange equation, right? Go around to this equation. Now that's d dt partial L partial r dot minus partial L partial r. Still equal to 0 since here it says force free. So no any other force. So that is this in this case. No conservative force and the other force, so that's equal to 0, then we are going to substitute that is d dt partial L partial dot is n r dot minus n r omega square equal to 0, or n r double dot minus n r omega square equal to 0. So m cancel, we have r double dot equal to r, or just put it, let me see. Yes, that is minus this one, okay. Minus n r omega square equal to 0. Can you solve this solution? It is really the standard second order differential equation. You know the solution, right? If a plus is sinusoidal function, is minus exponential, so the r immediately have this. I'm going to say this constant as initial condition, initial and exponential with omega, right? Here it's positive, it's real. Okay. So if you really want to have another one, which you already know, that is angle is always follow this the constant or uniform rotation. So that is the equation of motion. That gives us the speed at any time, where it is, the distance, and the angle, right? So if you look this one, what kind of trajectory you can see? You will see here at t equal to 0, we start from r naught. Then this is a positive term, right? So that means r will increase. So what that means? Means this speed, if you initiate r naught here, and it will increase all the work, right? So the trajectory is like this. Suppose the initiate r naught here, and you go with the rotation increase, right? With this trajectory, right? You can see the r increase outward, and then simultaneously also rotate. That is the rotation of this or equation of motion of the speed. So this is a second example that shows how we apply this Lagrange equation. There are several others. I think the homework I assigned, there's at least one you can play how to apply, and some example in the homework, in the textbook. Now we finish chapter 1. So let me briefly summarize the chapter 1, then we are going to go to the chapter 2. I said that the chapter 1 is go to introduce Lagrangian and derive the Lagrange equation, right? So how to introduce Lagrangian and derive Lagrange equation is from the volume principle. Right, that is key. And this principle is start from this horseshoe work, right? The force, net force on each side minus this, we call it the effect reverse force, which is dynamic linear momentum, and this horseshoe displacement equal to 0, right? We start from here. And then here we restrict ourselves, apply, and constraint, right? If you remember, do this. Then here we restrict as this all the work work done by this practical the force due to the constraint is equal to 0. Dot. Then we substitute into here, so we reach down is this one. All the applied force that is so-called here. Then to deal with this one, since we have a constant, we restrict this and all the constant is included in the general coordinates. So we replace this by introduce general coordinates. That is this one introduces since we need to consider the holonomic constraint, right? Then here, this one, by introduce this, and we also find this until finally we reach to, first we introduce Lagrangian, which is a function of general coordinates, general velocity, and maybe time explicit, depending on time or not. Then when we have this, so we have the equation, right? The equation of motion or dynamics for the system by solving this equal to now, there are two cases. 0, if the force applied equal to conservative, or equal to Puget prime, which is summation for I from 1 to n, and the force I non-conservative inner product is partial Ri, partial Pg. That is we reach. And we have some example to discuss this, how to apply this Lagrange equation, and you can see how to solve this. So that is the key is start from here. And this one, you will see is focus on this infinitesimal displacement, they call it virtual displacement. So this also sometimes they call differential principle. Now, alternately, Hamilton considered in the alternate way. Instead of look this differential principle, he considered a kind of entire motion of system during this time t1 to t2. This is considered as instantaneous time, right? As equilibrium. So now, chapter 2, we are going to discuss the so-called this variational principle or Hamilton's principle. So now, let's give the idea Then we introduce the second chapter. Or principle, or sometimes we call it integral principle. So you see, this is called the differential principle. That is start from the virtual work. Now, ultimately, Hamilton developed this Lagrange equation or analytical mechanics from the view of this integral principle or marginal principle during this year. Okay, so now let's go, what is the idea that we see something, the same system dynamics, we can see this from different view, right? So that's the first view, now let's look second view. So this one is considered this at instantaneous time, what is the infinitesimal change, or correspond to the infinitesimal displacement, what happened before this. Now, if the system from point 1, which is correspond T1, and move its motion with a time go to the 2, which is correspond T2 time. So this is a path, right? And what Hamilton considered, okay, let's look at some of the phenomena of the system, motion from 1 to 2, the entire motion of this path, not instantaneous time. So that is what he looking for. So now let's follow what is the consideration? Considerations. In this case, first, we consider the entire motion of the system instead of considering between T1 and T2. That is focus. And second, okay, we focus on a single function. Which function? L. So when Hamilton developed his principle, he already had a knowledge from D'Alembert, because D'Alembert introduced Lagrange. So he started from here. He interested to see, okay, this we include all the physical information of the system, and what we want to see is what happened of this L during the entire path. So that is what the focus, okay. Since L already defined this from the chapter 1, so that is based on the D'Alembert principle. So here, that includes all physical information of the system. That is very important. If not, we will not focus. So we are interested in L. Then what's the next? Okay, we will examine the line integral of L. What that means, line integral means, okay, so the system is start from 1 to 2, right? We have to do the integral, this we call the line integral as function time, since this is from T1 to T2. So he just looked this one. This is an important single functional which includes all the physical information about the system. Then let's see what happened. So we call this a line integral, and we interested focus on this. Okay, along the path. Now, so we introduce path instead of the virtual displacement. The path, okay. Now, when I say introduce path, maybe between 1 and 2 there are several lot of choices, right? So suppose it's actual path, we can have arbitrary virtual. Those are called virtual paths. It's all virtual paths. Suppose if we know the actual path is like, it's actual path. So what we are interested in to look this integral and see and apply, Okay. Then we are going to apply the variational principle. Apply the variational problem principle. To what? Okay. To study the infinitesimal change or virtual change of the I. This is integral. So we are going to see the change of this integral along different paths and see what happens. Okay, and then the number 5. So he will derive the principle that this will give us this. We can extract the all physical or dynamical information of the motion of system. That is idea. Okay, so that is the idea. We just alternated from another way. We look how about this entire motion system and just focus during this entire motion system. What is the behavior, or we call it also action of this Lagrangian? This is a single function, but include all the physical information. Then we look this line integral. How about the change in the line integral with respect to different paths? Then we expect from here, that is, we expect from looking this variation, then we can extract this all the information actually derived, finally we derived the Lagrange equation. That is final reach, like here. So from here, the virtual work, and then finally derive this. So all the dynamic problem can be solved or obtained from solving this one. And then he start from here, and finally, by looking this, he found that also get the same thing. So that is the second chapter 2, the first part of chapter 2. Then after that, we are going to extend the chapter 2, extend the Lagrange equation to in general. In particular, we know we cannot get the force due to the constraint, right? But we can apply this extend tool in general. We can have to get some information from there for certain conditions. So now that is chapter 2, and discuss conservation as well as introduce energy conflict. So now let's follow this idea, okay, and to derive this Hamilton's principle. What does it mean? So now, before that, we are going to have the terminology. Let's introduce some of terminology into we are going to use, right? Terminology. Okay, first concept or terminology we call the configuration space. Configuration space. What does it mean? We have several space. So now we introduce the configuration space. The configuration space is constructed by all the general coordinates. Basis. So, right, like xy coordinates, the Cartesian coordinates, we need x, y, z. Three these variables are independent of each other. Then we know the general coordinates are independent of each other, right? We already select. So now we are going to use those in general dimension, right? Dimension is n, right? 3n minus k. So because we know there are n general coordinates, they are independent, then they can build up, construct n space, n-dimensional space. So imagine if n is 1 dimension and 2 is 2 dimension. If we have big number, so you can imagine it's n dimension. So that is space is this dimension, and okay. So now, if I plot, we cannot plot n dimension, right? So assume that is just new configuration space. So the coordinates Q1, Q2, Q3, and O, right? Others, and also we have okay, yeah. So then any point, okay, that is point in this computation space. What does it mean? The point in the configuration space okay. It gives us the instantaneous state of system and the instantaneous instantaneous So here, this point is a function of all the Qj at t. Okay, because Q is function t. So at any instantaneous time, what is the status of system? That is represented by the point in the configuration space. Okay, so here t is parameter. This parameter controlled all because all the general quantities are function of time, right? So that is a parameter in the configuration space. Okay, then the paths. So now, how to define paths in the configuration space? So here, let me I use space here. Q1 and T1 and 2 and T2. So this is the path in the configuration space. The path in the configuration, okay, that is a system point, right? This is state of the also called the system point. System point is a point in the computer space. That point characterizes the state of the system at that instantaneous time t. Now then the path is the system point here travel in the configuration space during the time from T1 to T2, right? Travels in the configuration. Okay, that's the stage of the configuration space. T3, T1, that we cut the path. So this path, be careful, it is not equal to the actual path or actual path of the system. In the real space. In the real space, even for example, in a real space, right, I walk, right, along one dimension, one direction, this is a real path. But in the configuration path, it may be a curvature. It depends on how I selected the general coordinates, right? So that be careful when we say the path in the configuration space, it's not the actual path of a physical or the system in the real space. And therefore, okay, that's probably enough. Okay, good. So when we introduce this, now I think the terminology enough. Now we are going to discuss or introduce the Hamilton's principle. Before introduce the Hamilton's principle, we have another condition because Hamilton's principle only suitable for the system, specific system. We call this monogenic system. Okay, so that what is condition? The system should be monogenic system. So what is, now we're going to introduce this. You have question? Okay. There are two conditions. First, false. The false is required, right? The false, after this, the false exert on the system must be have a function, okay, in the system. The variable from generalized scalar potential. Or potential, yeah, okay. So that means here F is, let us consider potential first. So the scalar potential, V is two ways. Either only a function of general coordinates, maybe time, or is function of general coordinates and also the general velocity and time. Both are okay. So that is we call the scalar potential. Then that means if the system, the force exists on this system such that it is associated with or it is derived from the existence of scalar potential. Okay, so then the force, right? Because this, then we have the force formula. So the force, the GS component of force is the negative partial V. This is actually include all potential, right? If we consider in chapter 1, there's include external potential and interacting potential. That all the potential that exists, then the force E here is general coordinate. This is not the original coordinates. So that means we do not restrict to the original coordinates, but if we have the potential which is a function of general coordinates or general coordinate and general velocity, then we can find associated with this, the force is as a partial, is the derivative, right? Or in general, if this is only function this, right? So or for, in this case, we have two terms, partial V, partial QG, plus total time derivative of partial V, partial QG dot. Okay, so J is is all this degree until the total number of degree freedom. So that is case. This means the system in this case, all the force exert on systems we follow this. Then we have this now about the constraint. Another condition is to the constraint, the second one. Okay. Constraints must be holonomic. Holonomic. That means here. So that is the condition. Holonomic. So if the system has the force is this, and the constraint is holonomic, then we call the system is a monogenic system. And no system is considered suitable to apply to the Hamilton's principle. So this is something like this, the Allenberg principle. We introduce or restrict ourselves that all the constant force due to constant to the Russian work is zero. We ignore that term. Then we try to find this because then we can find all these independent general coordinates from this one, right? Which are independent Ri, but now if we have this non-holonomic constraint, we can find the independent general coordinates and to replace this. So that is why we need this. And this one is we need, you can see this are conserved force. So the Hamiltonian principle all considered conserved force. Now conserved force, we're going to discuss extended and see how they do this work. But the Allenberg has no such restriction, right? The Allenberg we derived the Lagrange equation either equal to 0 or that is for the conserved force. If non-conserved force, that equation is equal to the non-conserved generalized force. Okay? So see the difference. Okay. So once we have this, then okay. So all right. Once we introduce, then now we are going to describe the Hamilton's principle. This principle means okay. First, as I said, he focused on is introduce this the line integral, which we call I, which is a function of general coordinates, general velocity, but not time, since this integral is integral with respect to time t1 to t2, the Lagrangian, which is a function of general coordinates. General velocity and time and dt, right? So now we introduce this I, which we call the line integral. What is line integral? The line integral is the L Lagrangian integral the Lagrangian between the time t1 to t2 with respect to t. So after integral, the t variable disappears, right? And only function of general coordinates and general velocity. So that is introduced the line integral. And as I already said that the reason why we do this is it includes all the physical information, right? All physical. Okay. Then once we introduce this, the Hamilton's principle, mathematically, when we give a mathematical, I'm going to explain. Hamilton's principle 6. Principle, mathematically, this question is delta I change of this line integral. Okay. If this actual path along the actual path equal to 0. Very simple. That is his statement that the line integral, if the system is move or travel along the actual path, that's virtual derivative. This is also called the virtual derivative, right? Or displacement, but this displacement is with respect to the path, not the general coordinates. I erase, right? Oh, here. Yeah, I erase. So now we have the virtual displacement. See this one. respect to the actual path. And if this system is around the actual path, this integral will be 0. So what does it mean? It is statements like this. Statement. It's in the dynamics of physical system is determined by a variational problem. This is a variational problem for functional based on a single function. Okay, we need to expand this one. What does means? Okay, so that means here it's determined by, right? Determined by this variational problem of this functional L, and this variation, as I said, is correspond to the since it's a line integral, that is different paths. So that means among all the paths, among all the possible paths, the actual path, is the system. Okay. Okay. Along this path, the actual path, the system travel along the actual path. The system travels along the actual path. It's still not stationary. So that means we, from 1 to 2, actually we can have all the possible paths. But if the path is actual path, that system along this path is stationary. So what does mean stationary? Deviation is 0. Right, so that is this one. That is why we say that we select this. We are going to find all the line integral of this here. Then we are going to do the derivative and find the stationary. That means the deviation is 0. If that is 0, then that is the actual path. That is the actual system move along that path. So that is a statement of this Hamilton's principle or statement. Now we are going to see if we accept this principle, okay, what is L, the information, okay. So now the question is how to derive the physical or dynamic information. Information of system. That is, or how to extract information from this principle. Okay, so that is our next job. That, and as I mentioned, you will see at the end, we will derive we derive Lagrange equation. So now, in order to derive the physical information, extract physical or dynamic information from here, we need to remind us some physical or the mathematical scheme to help us. So we need the technique required to take required. We call this Euler Lagrange differential equation. Lagrange differential equation. Okay, let's go back. So what this means, let's first consider, simple case, consider one dimension, no function. Let's consider this and make it function f. Then we are going to extend to the more general case. So what is one-dimensional function? F is a function of y at y dot, but y is function of the parameter x. X. So x is parameter, y is functional parameter. We call this this is variable of the function f. So here y parameter x. Then what we see is for given x1, we have a y1, which is x1, and then another. Let's go to a path. So this is a y2, x2. So what this means, you can see here, y is a function x, but is a variable of the one-dimensional function, and this gives a path. That means how the path. Think about like a convolutional space. We have a general coordinate q, right? Q is a function time t. So if I compare with that, you will see x is like time, y like q. So then the q change or travel in the convolutional space give a path. And like here, the y as function of x, and with x change, it will give a path on this xy the plan. Then we're going to looking for this. So if this, then we are going to this y dot is dy total time total derivative of this y as a parameter x. Then we introduce line integral j to distinguish I here. So we use j, which is integral from x1 to x2, the function of f. And we know that is a variable y dot, and x, and do the integral with respect to the parameter x. So that is the Euler Lagrange differential equation. We are going to look this integral and see. So on Thursday, I'm going to discuss this. So how to make this. If this infinitesimal change or virtual change of this j is equal to 0, what kind of information we can get for the function f? Okay, that is the idea of the Hamilton. You can see the physicists, they always ask question and think about or like a critical thinking about themselves from their way, and see if it is nature, if it is nature law, different way will go to the same, right? Like is the law which is nature exists. If not, if you go to different result, then that's not hold true for the nature phenomenon. Okay, good. I think yeah, everybody signed. Okay, good. Thank you.
Okay, I have a question about that qualification. Basic question last time. Yeah, the poly,
Yeah,
the math
yeah,
and all.
yeah.
But I think the frictionless, so for this case, it doesn't rotate, so the values would be the same as,
So you have, but you have constraint here. Yeah, you
Yeah.
can select the one dimension and
Yeah.
cut this one, and you have a constraint. And this one, it says frictionless, massless.
yeah, at this point, they are the mass,
Oh, yes, mass. Okay, now they have a mass.
but
Most of the internal poly can be calculated. So they have they have rotation. This is the initial. Yeah.
but technically without friction, how does it? That's
That
why-
is okay. In this case, you see there's the torque is due to the weight. So the rotation not only the fractional.
Okay.
Does that make sense? So if a fractional, then have a so you have. So here, this has a, okay. This is like a force here, right? Let me say that's a force. This force generates the torque on this wheel, right? If I have a fractional, you have another force, and you have considered altogether. If I suppose there's a fractional force, then if I have a fractional force, if not, then only this one contributes to rotation. Right? So in this case, actually it's also rotate, but depending on the M1, M2, which one is, if they are same, then they balance. If not same, that makes sense?
Yeah, but without friction, like when the rope is in touch, like you have like that force is actually due to the normal contact force, like, but it doesn't like engage in the rotation of the pulley in this case. I thought over and over. I actually did the rotation part, then cut it off. And I'll try it back again.
Yeah, try that, yeah.
Yeah.
I think in this case, at least, when we have rotation, it has a non-zero top, right? But in this case, yes, we have a non-zero top. Of course, you have also this force. So you
Yeah,
have
but
a subtract
both
both.
the forces like
If they are equivalent, but if not equivalent,
yeah, but still to make the pulley rotate, like to interfere with the pulley, like the only two possible ways is either the friction or the contact force. So the contact force
yeah,
in
this
this
is
case,
contact force, yes.
yeah,
Or
but the
you
contact
can
force
the
becomes
tension, right? Something which is not tension.
yeah, but to make the pulley rotate, like to make the pulley rotate, we need the contact between the
Yes, yes.
and we can assume that there's contact, but then it becomes perpendicular compared to the pivot point. Like,
You can hear the contact, right?
here, there, and
Yeah.
in all the points, like compared to the pivot, the contact
You
force.
mean these two folds perpendicular, yes, but these two folds generate, no, the top is not cancel each other. Let me see, if this is a false, right? So that is, the top is pointing to this one, and this one, the top, yeah, they are opposite, but if not equal, then the night top is non-zero.
But the tension is not applied on the pulley because to apply that force on the pulley, you need the
Okay, I
Yeah.
understand what you mean.
Yeah.
Okay, now that is, if the force on the pulley, the night force, then that is if we, since this is substantial here, you do not consider weight, but if the weight is the center, whatever, so T minus plus T prime, that is zero, because there's no any other, no fractional force, so they cancel each other, right?
like
Ah.
even if they are not equal.
No, let's do this way.
Like,
no, this is a,
there's no
Imagine
way.
you consider not the pulley, you consider the rope or the strip,
yeah.
rope. At each intersection or rope, you have up T1 and T, right? Like this. But if this mass is at rest, then T prime equal to negative T. But if motion, it moves, It will not, right?
Yes, okay, but like that motion, can it make the pulley rotate? That's the issue. I thought
You mean this,
and that motion happens, and if there's no friction in the pulley, like is the thing, there's no way the pulley could rotate.
I know what you mean. Without the fractional, I think with fractional, without fractional, the only with fraction is you have the condition that at any point here there is no relative motion, so the fraction equal to this one, then you have this V equal to R over something, right? That is the condition for the with fractional without slipping. But but we have a slipping. If without fractional still have a slipping, that means the rule with respect to the edge of the poly, there's a slipping. But I think this still counts as a rotation if the net or net top on this, or is the rule.
With the contact, like always the contact is perpendicular to the pivot, so like at all the points, like here to here, let's assume the rope is in contact,
yeah.
so like if we get all the contact forces, so here, up to here all the contact forces become perpendicular, so it,
Okay, now you mean the normal force. Okay, you
Yeah.
consider this.
the more like I,
Yeah, that will not make any
yeah,
contribution.
and then
But this is a contribute. Those contribute this rotation. Because the force here, this top, right? I mean this moment arm, they are perpendicular.
yeah, okay, but my problem is that tension will not be applied on the pulley without friction, right? I mean that force.
That is, I think maybe my previous answer is not correct because you just think about this way. Okay, the loop itself motion and is without, oh no, it's not.
It's like if I draw the rope separately, even if we
Yeah,
have
yeah.
tension down like this.
But without contact, without fractional force is that. But without fractional force does not mean without contact, right? I think
yeah,
that is
like with
yeah.
Let's say if it was without friction and without contact, it just goes down.
Yeah, but we do
With
not
con-
say without contact,
Yeah,
just
with-
without fraction.
With contact, the only force applies like is still like the forces that are that like when it is in contact, the forces that get applied on the pulley are perpendicular, and so which doesn't create another torque without friction.
If you're talking about this force, that's fine. But this is also tension force.
Yeah, that's
Okay, I mean, let me consider, you are like go to the microscopic that there's no contact between the surface and the roof.
yeah. But even if there's contact, like without friction,
We have a force, but this force is not fractional force. If we consider this no fraction, just consider the surface. Without fraction, there's no fraction force, but still have some other force to make the motion. Does that make sense? You probably say that since no contraction, so the roof, the poly has no force,
I know even
exert force on poly, right?
I'm saying
That is what you think.
with the contact, the forces like I mean the only two.
Yeah, so that the contact, your question is what is the contact? If the fractionless is means without contact or only without fraction force. That is the two things, right? If without, if you say that fractional less means no fraction force, no contact, that is your conclusion.
For example, if we have a car or something on a frictionless surface, if we start the engine, then let's say we are rotating the wheels. If there's no friction now, still there's contact, so the car.
I know, yeah, that is you need let me think about your question. The contact. Contact is contact means as you say, the contact normal force, you consider normal force perpendicular to that, but that means you consider contact. So if a contact, then there's a force. Due to this, I mean the contact between the loop and the pulley. You mean the contact between loop and
But
pulley,
we are
right?
not attaching it.
The surface of the pulley.
Yeah, but that is perpendicular to the pivot. That's the problem. So then.
No. The force is from the pulley, from the rope. There's a tension, not perpendicular to the surface, not normal force. This is the contact. You mean the contact is one is this one, but that is at the rest. That is like okay. You consider this way. Interaction. I'm not sure this. Dr. James here. Interaction, so the pulley and the loop, if they have action interaction, yeah. Maybe next time.
Okay.
Don't want to record everything she said, so we can
Oh,
refer it next time.
that must be really
Because I'm interested in it too,
good.
Probably because I didn't.